party went well. We get 2 drinks allowed, and everybody being...
And the after party?
Yeah. Well, anyway, everybody had to be officially tagged that he or she that was on right? There were speakers that were very happy that they
Yeah. Yeah, it's been a while.
Anyway. Okay, let's continue with his 4th lecture.
All right. So, if you remember last time I introduced these 2 component spinners, lambda and lambda tilde, which are related to the momentum vectors through, we defined this 2-dimensional matrix K alpha alpha dot by contracting with the sigma matrices, and we saw that the determinant vanished if the K was massless, which allowed us to factorize it into these two component spinners, which are basically the same as the left and right-handed spinners you would have in the Dirac formalism, but kind of compressed down into 2-dimensional spinners. And I mentioned that the things that we usually work with are the invariant contractions between these 2-dimensional spinners of the same type. The right-handed one with the right-handed one with the Levi-Civita tensor gives this angle bracket, which is antisymmetric in the particle labels I and j because of the Levi-Civita tensor. And there's nothing that similarly for the left-handed spinners, we introduced this square bracket ij. And there's nothing that directly can be used to contract the left and right-handed spinners. You can put other stuff in between. So these things are antisymmetric and vanish if the particle label is the same for both arguments. And there's a momentum conservation relation. This thing in the middle here is really the sum over kj slash or kj alpha alpha dot. For example, for n equals 4, this is a very common identity you'd use to simplify things. If you put, say, 2 between 1 and 4, then using the fact that k2 is minus k1 minus k3 minus k4, you get this term, because the k1 term gives a 1, 1, which vanishes by this identity. The 4 term gives a 4, 4, which vanishes by this identity. So we'll see there's not really much you can write down in the 4-point case that is sort of invariant under some little group scaling we're going to talk about in a little bit. So I mentioned this, I derived this identity for you, which shows that these things are essentially the square roots of the normal Mandelstam variables or dot products up to some phase. One thing I didn't do last time was derive the last useful identity, which is, actually I have to check my notes, make sure I got that sign right. But anyway, if you take and contract them, 4 spinners in this order, and then you swap 2 of them like that with a minus sign, you get this other combination here. This is easy exercise to derive. You can derive this by starting with the property that if I take 2 spinners, lambda I and lambda j, think of them as two-dimensional vectors. If you just have a bunch of 2-dimensional vectors, you know that once you have more than 2 of them, they have to be linearly dependent, because the biggest basis you can have in the 2-dimensional space is 2. So you can expand this spinner. Maybe I should put an alpha on it. And then these coefficients are numbers. You can work out what these numbers are. They will be ratios of spinner products by contracting this equation with lambda I and lambda j. You can work out what these coefficients are. And then after you know what C1 and C2 are, you can contract with lambda L, and you'll derive this equation. So this is a handy identity. So now we want to make use of these spinners to discuss how we can make sense out of the simplest scattering amplitude, in some sense, the 3-point amplitude. The thing about the 3-point amplitude for 3 massless particles is that if all the vectors are real, it doesn't really make any sense. So if we have 3 vectors, k1, k2, and k3, that sum up to 0. Then all of the Sij's, which can also be written as ki plus kj squared, they're equal to the third guy squared. So they all vanish. So we can't sort of build any kinematic variables out of the Sij's. Let's see. We also have the we can't build any non-vanishing invariance. And if we write these as 2ki.kj and parameterize ki and kj as in terms of energies and angles, we have this familiar formula that the only way we can make these vanish, either you set one of the momenta exactly to 0, say k3 equals 0, and k1 is minus k2, which is singular. So that's sort of, or you can have a strictly exactly collinear configuration. But in either of these configurations, the spinor products ij and the spinor products ij will all be equal to 0. So with real momenta, we just can't find any kinematic variables for the three-point process to depend on. But if the momenta are complex, we'll see that we can define that. And just heuristically, suppose we take this in. We like to think of k1 as outgoing, but let me just say that minus k1 is incoming, and it's coming in along the z direction. And then we can split it up into something like this. So now these vectors are no longer parallel. They're still light-like. This one is light-like because this momentum squared minus this one is 0. This minus this squared is 0. And then this is 0 because it's a space-like vector. So it would be minus 1 squared minus I squared. So that cancels this. So by using complex momenta, and then we can have it add up properly by adding another term. Sorry, that should be a plus 1. So these two vectors add up to this. Both of them are light-like. And the way we got it to work and not have them be parallel vectors was by extending them to make them complex. In fact, back in the 1960s, when the use of complex analyticity was in its heyday, somebody once remarked that the greatest discovery in particle theory in the 1960s was that of the complex plane. So, still true that it's very useful. Let's now, but what we want to do now is not use something quite as explicit as this, but let's find two solutions that satisfy the complex on-shell kinematics for the three-point process. So one solution is that we take lambda 1 to be proportional to lambda 2, and the proportionality constants are a little bit arbitrary, and proportional to lambda 3. So all three of the lambda tildes are proportional to each other. Then all of the square brackets vanish. But this little example suggests, and it's true, that we can have the ij's, these guys, be non-vanishing. In other words, we have to have the products always vanishing. Okay? All three of the Sij's, S12, S23, S31, have to vanish. But that doesn't mean that all of these angle brackets have to vanish. if the momenta are real and these are complex conjugates and they're square roots, then if this is 0, these guys have to be 0 too. But we're breaking that. We're making the momenta complex, so these aren't conjugates of each other. So the lambda tildes can be parallel, causing all of these things to vanish. And yet we can still have these be non-zero. And then there's the conjugate kinematic case, where we take lambda, all the lambdas to be parallel. Okay, any questions about that? It's kind of a simple thing, but it makes it possible to do things like BCFW recursion relations in a nice uniform way, where when we factorize amplitudes, like I was talking about before, we can actually factorize them onto 3-point poles in the complex plane, utilizing some simple 3-point amplitudes that we have for all theories under consideration. Okay, now I need to mention something which is kind of called little group scaling. So we have some scattering amplitude, and we have a particle coming out of here with helicity h. And if we imagine rotating around that, because it carries angular momentum, if we rotate azimuthally, we should pick up some phases. And these phases are carried by the spinor products, because the spinor products also serve as the wave functions. I mentioned that the lambdas and lambda tildes are spinors for helicity plus or minus a half fermion. And if you look at the Feynman rules so we want to scale lambda goes to, doesn't really matter what, EI lambda tilde goes to the opposite direction. And we want to make sure that our amplitude transforms correctly by putting the right number of lambdas or lambda tildes on the outside of it. So for h equals plus a half fermion, the wave function factor turns out to be lambda tilde. And then this scales, it's not numerically equal to, but it scales in the opposite direction as 1 over lambda. Whereas a helicity plus minus a half fermion has a wave function the opposite handedness, which scales like lambda. And the scaling should be twice as big for a spin 1 particle, which has helicity plus 1, as for the fermion case. And so the wave functions for a helicity plus 1 vector state should sort of have twice this scaling. And in practice, the way we accomplish that is by writing down for the ith particle a polarization vector for a plus helicity. And I'm going to write it in the alpha alpha dot version, where I've contracted it with the Pauli matrix. And there's a dependence on some arbitrary vector q. And up to factors of root 2 and stuff, which I'm not going to be too careful about here. We need to put a spinor lambda tilde alpha dot in the numerator to get half of this scaling. And we need to put a lambda in the denominator. And we'll use the spinor, this is called a reference spinor. And this could also be written as Q alpha lambda alpha dot I over the angle bracket IQ. So Q is a reference spinner. You shouldn't choose it equal to K to the momentum or correspond to the same spinner here, or you'll get a singularity. Different choices of Q are equivalent to on-shell gauge transformations, where you shift the polarization by something proportional to the vector and it doesn't change anything. The thing to check is that this thing is transverse. That's a requirement for a photon or a gluon or whatever vector polarization vector. So you can check that, for example, epsilon mu, k mu, is epsilon alpha dot, k alpha alpha dot, and ki. And because we have a lambda, this will be proportional to a lambda alpha dot I from here. And there's also a lambda tilde alpha I dot in here with the upstairs index, which would be equivalent to writing it as a beta dot with this. So inside this product, there's a product of two identical right-handed spinners, which are zero by the anti-symmetry. So we've checked that this thing's zero. It has an extra benefit. Sometimes if you're doing explicit calculations, you can check that epsilon.q is also equal to 0. But I'm not going to really use that much. Instead, I'm just going to use the fact that it scales like 1 over lambda I squared. Well, I kind of put that in. I said it should scale like that because it has twice the angular momentum of the fermion state. And then the h equals -1 vector won't be too surprising. It'll be you kind of just conjugate everything. And that will scale like 2 powers of lambda upstairs. So in general, the scaling in a general amplitude that depends on a bunch of lambda i's, lambda I tildes, it has to scale like lambda I to the -2 hi. And because lambda tilde scales the opposite direction, every time you see a lambda tilde, it counts. You just remember that it counts in the opposite direction. Now in the 3-point, and this is actually extremely useful for checking your algebra, because if you do something complicated and you have many terms, and you screw something up in one term, it won't scale the right way, and then you'll know which term you screwed up. But never mind that. Let's talk about the 3-point process. The 3-point process cannot depend both on the lambdas and the lambda tildes, because we have two choices of complex kinematics, and in one of them all the spinner products involving the lambda tildes vanish. So let's work in that kinematics, and then let's just ask if we only have 3 different invariants we can work with, and so the tree level 3-point amplitude for a state for particles 1, 2, and 3 with helicities h1, h2, h3 must be proportional to 1, 2, This is true for any particles, spin 0, spin a half, spin 1, spin 2. So it has to scale this way. Let's just check that I didn't make an algebra error. Look at this scaling with lambda 1. It comes up in 2 places. And here I have an H3. Here I have a minus H3. So that cancels. Here I have a minus H2. Here I have a plus H2. And that cancels. Here I have a minus H1. That builds up the minus 2H1 I want. And the rest sort of follows by permuting labels around. Okay, so this is very general form for any 3-point amplitude, just depending on the helicities. So let's work out a simple example. What if we're in Yangmills theory? All 3 HIs are equal to minus 1. So then we'll find that A3 tree, just plugging in over there, so the question is, could the Yangmills amplitude for 3 negative helicity gluons have this form? That's what's dictated by this formula. The answer is no. Can anybody guess why? Who hasn't seen this before? There's one thing we're forgetting. The thing we're forgetting is to think about dimensional analysis and what the dimension of this coupling should be. Or to say it another way, let's at least, we're trying to do all this without actually even evaluating this very simplest Feynman diagram, the 3-point diagram. But let us notice, you remember that this 3-point vertex scaled like k to 1 power. It's linear in the momentum, and it had those Minkowski contractions. It had like eta mu1, mu2, k1 minus k2, mu3 times FABC. So it has, dimensionally, it has 1 power of the momentum. Now, how do these lambdas scale? Well, we know that lambda lambda tilde is k, so lambda scales like, I just put in braces to indicate dimensionally, is k to the 1/2. Or ij, they scale like k dimensionally. Yeah. So this thing goes like k cubed, because we have 3 of these spinor products. Whereas this goes like k to the 1. So it's not really the right dimension to have a dimensionless coupling in front of it. What it really is this is a matrix element of a higher dimension local operator that's gauge invariant. So this actually is an amplitude for where this operator here is FABC times F mu rho A F B nu rho F C rho mu. Okay, so you take the field strengths, contract them cyclically like this, and put in a FABC. And this is a dimension 6 operator, so we usually put some mass in the denominator. So that would produce an amplitude that looks something like this. I've stripped off the color factors, remember. By the way, when I wrote this down, there's probably something else I should check. If I want to assert that it comes from something which has a FABC vertex, what should I check to make sure it's compatible with having an FABC in front of it? Yeah, the symmetry, great. So we know that when we produce a gluon, say, it's a boson. So the amplitude has to be symmetric. under exchange of any two bosons. But that symmetry can be accomplished by having it be either symmetric in kinematics and symmetric in color, or antisymmetric in kinematics and antisymmetric in color. And I got to figure out which one it is. So what I do is I look at this thing, and I exchange two labels. Let's say exchange 1 and 2. Whoops. And I get 2, 1, 1, 3, 3, 2. And then I reverse you see what I did? I just swapped 2 and 1 and 2 in here. But now I use the antisymmetry of the spinor products to rewrite it as 1, 2, 2, 3, 3, 1, at the price of 3 minus signs. So I pick up a minus sign. So this kinematic structure is totally antisymmetric. And therefore, it's compatible with being multiplied by the totally antisymmetric color factor. Well, that was great. We wrote down the wrong amplitude. So, in fact, we now know that in Yangmills, minus 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 equals 0. So let's try again. We'll switch this guy over to plus. So this has to scale like 1, 2 cubed, because this is now plus 1, and then these two minus 1s have minuses in front of them. And then 2, 3 to minus 1, 3, 1 to the minus 1. Well, that's basically the right formula. It's just sort of conventional to rewrite it as 1 minus, 2 minus, 3 plus. Oftentimes people put an I out front. That doesn't matter too much. And it's nice to have this nice denominator whose symmetry properties you know. And then you see there's this factor of 1, 2 to the 4th in here. And that's one of the two 3-point amplitudes of Yang-Mills theory. And it has support on the complex kinematics where these guys are non-zero. But there's a conjugate kinematics I only gave you the formulas where 1 and 2 were negative, but if you change them to be 1 and 3, then this changes to 1, 3, and this stays the same, and so on. These are also known as the 3-point examples of the Park-Taylor formula. So let me just write down the Park-Taylor formula. For MHV. So that formula says that AN tree, we'll just call it, we'll call this AN MHV and label it by two lines, say J and K. And so that refers to the n-gluon tree amplitude with almost every guy plus. So I'm just giving you this formula now. Later when we do the BCFW recursion relations, we'll use them to prove this formula recursively, inductively, using the initial condition, which is also what you get if you just plug in n equals 3 in this formula. So there are n denominator factors here, which are just the spinor products formed by the cyclically adjacent gluons from 1, 2 to 2, 3, all the way around to n1. And then there's a factor which always has 4 powers of the spinor product between the only two negative helicity gluons. The rest of the gluons in this formula are meant to be positive. So if you specialize to n equals 3, you just get 3 of these factors in the denominator. And if you take the 2 negative helicity guys to be 1 and 2, you get this. So we saw just by very simple angular momentum scaling type arguments, we kind of derived the structure of the 3-point version of the Park-Taylor amplitudes. Maybe you should show one more thing, which is, I don't want to lose that one just yet. That's enough for now, maybe. So let's now suppose we have gravity. From the formula I just erased, which had the helicity dependence, since it was kind of linear in all the helicities, if we scale everything up by a factor of 2, we can ask whether there's a M1 minus minus, that is something with 2 negative helicity, helicity minus 2 for each particle. That would be something that would go like the square of the same object we wrote down for Yang-Mills theory. So this has the right scaling, but again, we got to check the dimension. And the Einstein-Lagrangian gives a k-squared dependence if you work it out, because the Riemann tensor is sort of a derivative of a Christoffel symbol, which already has a derivative of a metric. So Einstein gives k-squared, but this thing goes like k to the 6th. So once again, this does not have the right dimension to correspond to a 3-point scattering amplitude for gravitons in Einstein gravity. And once again, it's a matrix element of some operator, which is often called R cubed. But it's basically something like that is, the Riemann tensor can be thought of where you divide the two indices into two types. And we're going to trace over some types which are shown hidden, thinking of this as a matrix on the other two indices. And so these are not the this is really the Riemann tensor. But I'm hiding 2 of its indices. Anyway, there's a way of contracting the visible 2 indices cyclically like this. And we don't have any FABCs in gravity, right? Gravitons don't have any color. So we don't have any color structure to make antisymmetric. Gravitons are bosons. So this thing had better be symmetric under permutations, and it is. So it is the right thing to describe a graviton amplitude, just not the one for Einstein's action, the ones for matrix elements of a higher dimension operator that has a 1 over sort of m to the, well, anyway, it's a dimension, it's appropriate for something coming in at 2-loop higher order, actually. Okay, but we can do the same trick and find the gravity amplitudes. So for real gravity, Einstein gravity, we have that M3 tree. Well, rather than just rewrite the square, I'll just, it's just the Yangmills squared. So this is the first indication that gravity should just be the square of Yangmills somehow. We can maintain that concept beyond the 3-point function. Okay, so now, are there any questions on this? Yep.
So you gave the sort of the 3-point amplitude.
Yeah. Yeah, I think this was actually noticed by Nair way back in the 80s, soon after the Park-Taylor formula came out, and so there's a certain connection which I think also is behind the scattering equations at higher points. So there is a connection there. Yep. Yeah.
Why they are just formally they are exactly the same.
Yeah, like the formula for the 3-point function is dependence on the separations. Well, I think it comes from the same scaling behavior. I mean, I was describing these scalings as if they were azimuthal, but you can also scale the lambdas, not conjugate. Maybe that's actually a little better way to do it. Scale the lambdas and lambda tildes independently in general. So I think it's probably happens to be the same as the conformal symmetry, but I can't. Maybe I should probably think about this a little more before trying to answer it better. I mean, let me say that if you go beyond the 3-point case, I think you have a different situation in terms of the counting of the number and things you can write down in the amplitude case is different from the sort of cross ratio counting that you get in the 4-point case. So I think it's kind of an accident, in some sense, maybe a little bit of an accident for a 3-point case. Any other questions? Okay, so now we're going to talk about the BCF W recursion relations. And the basic idea is that we want to, it all relies on factorization. So this sort of picture, since the particles are very generic in this formula, I'll just draw them as straight lines and not gluons. But the idea was that in the region where this intermediate momentum goes to 0, we know what the answer is, that it factorizes into two pieces. So I think we had, last time we had p plus 1 lines coming out of here, and n minus p plus 1 lines out of here, and the an in this limit where k squared goes to 0 goes like an minus p plus 1 usually there's an I here. So this is a statement about the amplitude, which is in principle a function of many different complex variables if we're treating the momenta as complex. The thing is, physicists do not understand multivariable complex analysis. Most mathematicians don't understand it either, or they think it's trivial, one of the two. So, were we having this discussion yesterday after 2 beers? So, which was the limit, I remind you. So the point of BCFW was to say, I don't need to know multivariable complex analysis. I just need to know Cauchy's theorem for one variable complex analysis. If I just consider deforming in a specific way in which I only have to deal with one complex variable. So what we want to do is we want to find a family, a one-parameter family of amplitudes that depend on a complex parameter z. And the original amplitude will be when we set z back to 0 again. So this is called the BCFW shift parameter. And there are many different choices, but the easiest one is the one that was used in the original paper. So let's just write that down. It's called the 2-line shift. We could label this N1 for a reason we'll see in a second. So what it does is it takes lambda n tilde, the square bracket kind of lambda of n guy, and takes it to a new variable, which is usually denoted with a hat, which is the old variable minus z times the spinner for lambda 1, the conjugate spinner. And it leaves lambda n alone. And then it takes lambda 1 and transforms it to lambda 1 hat, which is lambda 1 plus z lambda n, and leaves lambda 1 tilde alone. So the point of doing that is that we have 3 conditions we want to maintain. So we want k1 squared and kn squared in the shifted variables to stay on shell. But that's actually pretty manifest, because to make them on shell, we just have to say that these are defined by a factorized 2x2 matrix, and then the determinant will vanish. And so k1 hat alpha alpha dot, but I'm not going to write that. It's just the new lambda 1 hat times lambda 1 tilde, but it's still factorized. And then same thing for kn hat. It's the old lambda n, but the new lambda n tilde, but it's still factorized. So, but when we shift the spinners, it's automatic that the external legs stay on shell. But the precise form of the shift is required to maintain momentum conservation. We don't want to touch any of the other lines in the 2-line shift, and therefore the sum of k1 plus kn should remain the same. And it goes to, well, now I'm going to write out what the lambda 1 hat is. It's lambda 1 plus z lambda n. Lambda 1 tilde stayed the same, plus lambda n times lambda n minus z lambda 1 tilde. So the plus z and the minus z here are just designed to ensure that these two terms cancel, because they both have plus or minus z, lambda n, lambda 1 tilde. And the original terms are just what we had before. So that's why the shift has this form, to maintain momentum conservation. The thing that they're shifted by, if we had a vector, they would be shifted by, if we wrote it in terms of view, of a 4-vector. So V mu is proportional to gamma matrix or sigma matrix stuck in between two spinners, 1 and n. And using the Dirac equation, you can see that this vector is perpendicular to k1, because k1 slash equals 0 can be applied this way. It's also perpendicular to kn. So if we imagine that k1 and kn are coming in like this, then V is some vector that points off in some orthogonal direction. And but on the other hand, you can also check that V squared equals 0. And the only way to do this is if V is complex. So it's similar to what I was talking about in the 3-point case. We take advantage of that complex kinematics intrinsically here to be able to shift the vectors and still keep them on shell. Okay. Now we need to, now what we want to do is apply Cauchy's theorem. So what we're going to do is write down 0 is the integral dz of an of z over z. And we would like this to be an of 0 plus a sum over k times the residue of an of z over z at z equals zk. The picture that goes along with this is that here's the z-plane. I'm putting in a integral of not just a, but a over z, in order that the z equals 0 residue gives me back the original amplitude. And then I'm anticipating some poles at finite location zk. And I'm going to take this large circle out to infinity. So this is only true if an of z falls off, goes to 0 as z goes to infinity. This is called checking the boundary terms in the BCFW relation. So the simplest way to ensure this, I mean, it's sufficient, it turns out not to be necessary, is to let n have helicity minus, and 1 have helicity plus. That will give us the best behavior of the external states, because epsilon n goes like lambda n over lambda n tilde. We look over here, lambda n stays the same, whereas lambda n tilde is going to get a large z dependence when we go to very large z, because lambda n tilde gets replaced by this combination at a large z that dominates. So this guy goes like 1 over z, and epsilon 1 plus has the opposite dependence. It has a lambda 1 tilde in the numerator and a lambda 1 in the denominator, but we're treating lambda 1 in the conjugate way, so this guy also goes like 1 over z. So this is the best behavior of the polarization vectors on the outside. Now we're going to look at a generic Feynman graph. And count powers of z. So because of this choice, we got a 1 over z from the wave functions. What about this vertex? How does this vertex go with the momenta? Right, it's linear with the momenta. And the momentum flowing along that line is the momentum being shifted. None of the other legs are getting shifted, but there's momentum flowing along this line. And the momentum that gets shifted is something like lambda n or lambda 1. It's proportional to z. So this vertex is proportional to k, which instead is proportional to z. Now in the denominator, we have a kind of a 1 over k squared. You might think that this goes like 1 over z squared, but it doesn't. It actually goes like 1 over z. And that's because the thing we're shifting by squares to 0. In other words, a large momenta k is this shifted thing, which is the shifted amount is z lambda n lambda 1 tilde plus some other constant vector. So then we're going to square this. But the leading cross term is where we take the contraction of lambda n lambda 1 tilde with k0. Because when we square this, we get things like lambda n contracted with lambda n, which is 0, or lambda 1 tilde. So this scales like just 1 power of 1 over z. There might be 4-point vertices. However, they don't have any scaling with the momenta, so they only make things better. If we have a 4-point vertex, things just get better. So the worst case is a bunch of 3-point vertices along here. And every time we put in a 3-point vertex, it costs us a power of z. But then we get the power of z back in the next propagator. So all the vertices and propagators cancel each other out, except there's one more vertex than there was propagators. So we end up with a leftover factor of z. But then these wave function factors come in and save the day and give us a z squared, 1 from each side. Goes like 1 over z. So with this choice here, we have satisfied this criterion that the amplitude should fall off at large z. Now it turns out that the cases where n is plus and 1 is plus and n is minus and 1 is minus, they're also okay. It's just you can't see that from the Feynman diagram argument. You need more sophisticated arguments to learn that. So 3 out of the 4 cases are okay, and the case n plus 1 minus is bad and doesn't converge out at infinity. Okay, so now we understand the behavior at z equals infinity. We have to ask where did these residues at finite zk come from, and we need to evaluate them. So So they come from the kth factorization. So here's one where I put a hat on it to remind myself that that momentum is getting shifted. And I imagine that k particles are on this side of the shift. And this particle going down here in the complex momentum will have a composite momentum, which is K1 plus K2 plus, well, probably bad choice of index here, but anyway, if I put a hat on it too, that comes just from shifting this guy, because these guys don't get shifted. And the ZK must be where this guy, the shifted guy, goes on shell. That's where we get to factorize the amplitude into two subamplitudes. Because at that point, the causality tells us, even though this is kind of in a complex direction, that these two amplitudes should not know about each other, and so they should that we should get a residue which is proportional to the product of the two amplitudes. So if we write 0 equals K1 hat of ZK plus K2 plus KK squared, it's ZK lambda n lambda 1 plus the so this was the shifted part of K1, and this is the unshifted part. As in the large Z analysis, the squared term doesn't contribute, and this becomes something we can write as I should probably explain this notation. If I have a vector V, which is a sum of massless vectors Vi, then I define A, V, B to be the sum of AV for the VIs, the sum of these spinor products. In four-component notation, this would be particular spinors, and this would be sum of the slashed momenta inside of V. So that's what this notation means. So then we just solve for ZK. So now we know where the residue is, and we just need to calculate the residue using the we use this formula over here. These guys are going to get evaluated at the shifted momentum, evaluated at ZK, and the last thing we need to do is to, this thing in complex kinematics vanishes, and that's what's going to give us our residue. We also had a factor of Z in the denominator, so we need to multiply Z by K squared. So the last thing we need to do to calculate the residue is to expand Z times K squared 1K of Z. And that you can work out. The Z is just proportional to ZK, and when you sort of work slightly to higher orders here, you get a factor of the same NK 1K 1 and Z minus ZK. Well, so this thing here is just minus the unshifted momenta going down that propagator, K1, K squared. So the final result is that from plugging into Cauchy's theorem is that AN or AN0 as a double sum. The first sum is just to remember that in, say, gauge theory, there's two gluon helicities that can go down that pipe. And then there's a sum over the allowed k's running from 2 to n minus 2, ak plus 1, evaluated at the shifted momentum k1. The rest of these are unshifted until you get to the last one, which is this sort of composite momentum. I guess the way I define it, I might have the arrow backwards. Here I refer to this as minus k1 with helicity minus h. This k1 k squared came from this calculation here. And then no, I guess I defined it the right way, coming down this way. So the hats are on two legs of each of the lower point amplitudes. Okay, this should have k plus 1 legs, and this should have n minus k plus 1 legs. So this is the BCFW recursion relation. And it's quite nice. It lets you work out amplitudes either by hand in the simplest cases. In Mathematica, you can code it up very easily. It underlies this method called on-shell diagrams at higher loop orders too. And you can implement it numerically on the computer pretty quickly. Maybe not quite as quickly as some other older formulas, but it works very well. So any questions about the derivation? One thing we can do very quickly with it, I'm going to cheat a little bit. I'm going to assume that an tree 1 plus n plus is equal to 0, and then show that so we can use the BCFW recursion relation to show that this one's 0, the case with 1 minus, given that the one with 1 plus, with all pluses, is 0. So we want to just draw the diagrams that enter into this relation and use helicity conservation. Sorry, the fact that when you cross the intermediate state, you have to flip the helicity. We can use that to quickly show that all the diagrams vanish. And therefore that the result vanishes. So let's first draw the generic BCFW diagram for this case. Let me erase something and do it over here. There's a special case with n equals 3, so we'll have to handle the, in general, you have to handle the endpoints of the BCFW recursion relations. So those are the cases k equals 2 and k equals n minus 2. If you look at that diagram, when k is equal to 2, the bottom blob is a 3-point blob. And you have to be careful about using arguments in that case, because when you have 4 or more particles in the blob, well, we're going to first show that it vanishes with 1 minus. Once you know, I skipped something, so I didn't have to worry about the all plus case, but it's true that that vanishes. Then we're going to show it vanishes with 1 minus. From then on, whenever you apply it, you need at least 2 minuses in every amplitude except the 3-point case. I think that's what you're maybe referring to. The 3-point case is special because we saw that there are 3-point amplitudes that are non-vanishing that have only one minus. Yeah. So yeah, that you definitely have to consider that as a special case. Good point. So first, the easy generic case. We have something with all pluses except one minus, and then we ask what can we put in here that makes both sides non-vanishing, and the answer is that we would have to we can't put a plus here because we already assumed that this blob has to have one minus. So then we come down here, and we have a amplitude. Let's see. Yeah. So now we have an amplitude that has two 1 minus amplitudes, but this is 0 by induction. In other words, we assume that it's true for every case starting with n equals 4. We're going to come back to n equals 4 in a second. But we should. That's just the generic diagram. We should also sort of double check the endpoints. Yeah, maybe I'm walking towards some danger here. Well, if we're at large n, this diagram is also 0 by induction. The case we really have to worry about, so this 0 by induction. The case we really have to worry about is the n equals 4 case. There's another case with the blob at the top, with the 3-point blob near the top. Maybe we should look at that one. We're going to deal with this in the same way we deal with the n equals 4 case. Let's do the n equals 4 case. In the n equals 4 case, the most dangerous case, we have a minus and a plus and a plus and a minus and a plus. So this amplitude here is proportional to square brackets, and this one is proportional to square brackets too. So the way we get saved is because the complex factorization for one of these two requires all the square brackets to vanish on that side. And how do we remember which one it is? Well, we remember that we shifted lambda n tilde was shifted. And because we didn't touch lambda n, that means that up here, the ij's must be the same, must be non-vanishing, because we didn't touch the right-handed spinners, which make up the ij's. We only touched the left-handed spinners, which make up the ij bars. And we know this thing is on shell, and so in the shifted kinematics where we're supposed to evaluate this blob, this one goes to 0. This one turns out to be non-zero because it's on the other side, but this thing goes to 0. So that causes this to be 0. In other words, you can have something that naively looks like a good factorization, but when you look a little closer, it has the wrong complex kinematics for that 3-point amplitude to be non-zero. And in the n greater than 4 example, it saves us here, too, that this upper blob is 0. OK, so we managed to show, although maybe it went by a little fast, that the case with 1 minus is 0. And so the first non-trivial case for tree-level gluon scattering is with 2 negative helicities. And we had written down the Park-Taylor formula for it. And you can run the recursion relation again. And in fact, let me save a little time. Let me ask what happens for the generic diagram if I now make one of these guys negative. But now I know this thing vanishes. This blob vanishes. And so, with 1 minus. So I can't get any contribution like this. If I'm to have any hope of a contribution at all, from as far as the lower blob goes, I need to have the negative helicity guy be down here. Now I have 2 negative helicities. I can use induction and plug in the Park-Taylor formula for lower values of n. Oops, I don't have enough negative helicities up top. So this side is 0. So this generic factorization still vanishes in the case that I have 2 negative helicities. And the only contribution is going to come from the endpoint. And for the same reason as here, it doesn't come from an upper endpoint. It comes from the lower endpoint, the case k equals 2. So we're taking the MHV amplitude and we're trying to prove that it's true. There's only one diagram to evaluate, which is the k equals 2 diagram, where we have 1 plus hat 2 plus. I'm assuming j that the other negative helicity guy isn't equal to 2, that it's up here somewhere. There are a whole bunch of pluses up here. This is leg k plus 1. Oops, sorry. This is leg 3. And then n hat minus. So now we're actually going to get a non-zero result. We need to know what the formula is for this blob down below. So this is A3 1 plus 2 plus minus k hat minus. And I wrote down that 3-point formula for you. All right. This is the 3-point formula that I wrote down before with 2 pluses and a minus, which has only square brackets in it. And it has sort of 4 powers up here. I have to plug in the shifted momentum 1 and the shifted momentum k hat. However, the shift of 1 is only in the angle bracket direction, the lambda 1, not lambda 1 tilde. So I can take the hats off the 1 everywhere. And maybe I get something like 1, 2 cubed over 2 k hat, the intermediate momentum, k hat 1. So that's what I'm going to plug in for this A3 down below. And then there's a AN minus 1 up above, where I'm going to plug in the Park-Taylor formula for the n minus 1 point case. So this factor is I, j, n hat to the 4th divided by the cyclic combination of the denominators down here, which start with k hat and then go to 3, go to 4, n minus 1, n hat, k hat. And I can take the hats off the n for the same reason I could take the hats off the 1. So we have this thing we want to show, which is whether the endpoint formula is reproduced by this one BCFW term. So I'm just rewriting this thing here, taking hats off. And then I get a 1 over S12. That's the unshifted pole in the BCFW formula. And then I get this 1, 2, this factor over here. And the only thing left then is to try to figure out how to evaluate these. I forgot to put in, I'm going to move a factor of n k hat over here, and another factor of k hat 3 over here. And I'm not paying attention to minus signs, so I'm just going to switch these guys around. So the only real thing you have to evaluate is something like n. This factor here can be rewritten as n k hat 2. And k hat has composed of the momenta 1 plus 2. And then it gets shifted by z, which is evaluated at the point z2. But that shift was proportional to lambda n. So it turns out I don't even need to know what z2 is. And so this 2 k2 slash or 2 bracket is 0. So I just get this simple factor here. And similarly, 3 k hat 1 just works out to be 3 2 2 1. So if you plug in for these factors, you see that almost everything is angle brackets. Also, S12 is 1 2 2 1. Almost everything is angle brackets, except there's a 2 1 here, and then there's 2 1 1 2 here, but there are 3 in the numerator. So these things all cancel, and you're just left with a bunch of angle brackets, and you can work it out that it reassembles into the correct formula. So just in time, we confirm the MHV amplitude. Thanks. Any questions? Quick questions, I guess. Yeah, okay. What's the combinatorial complexity of the on-shell recursion relations? I'm not very into computational complexity, frankly, because in the limit of a large number of n, we're all dead. So I don't remember the answer. But it's not bad. It's pretty pretty good. It's a lot better than Feynman diagrams.